Hello everyone. Here's a lesson on part 3 of the project. It's due April 13th. Please make a PDF of a draft of your answers to part 3 and submit those through Canvas. In statistics, there's always some risk that you're going to come to a bad conclusion because the sample that you drew was taken randomly. So there's always some chance that your results are some kind of fluke results that is going to cause you to come to a bad conclusion. Anytime you come to a wrong conclusion where the conclusion in your statistics disagrees with reality, we call that an error. And there's two kinds of errors. You can see them here. The first one is when you reject the null hypothesis, and that was wrong because the null hypothesis was true. And then the second scenario is when you don't reject the null hypothesis, but you should have the null hypothesis is false. So I'm going to work through an example. I chose to do the zombie apocalypse here. And I don't know if you guys know this, but there's zombies that go to school with you. Apparently 24% of the JCCC students have been zombies. And then when new students come in, the previous students infect the new students with this zombieism. But because school's closed and everything's all closed down, I actually think that the rate of zombie here is going to be decreased. So I wrote the hypotheses. Here are the two basic interpretations of the types of errors in the zombie apocalypse example. So the first type would be we would be claiming that the rate of zombie has really decreased. So we're going to claim that it's actually less than 24%, and that's wrong. Type 1 error would be if you said that it's less than 24%, but it really is 24%. And a type 2 error would be if you don't say that the rate is less than 24%, but in reality it really is. Let's connect the real-world interpretation of these types of errors to these sort of technical conclusions that we made already. So a type 1 error in this case would be if we say that the isolation is actually decreasing zombies when it's not. And a type 2, we would say that the isolation is not decreasing zombies, but it really is. So let's think about what some of the real-world consequences of this would be. So if we say the isolation is decreasing zombies and it's not, then what this means is everyone is like, yay, the isolation is decreasing the number of zombies. Let's just continue on with our isolation, and it's not going to do anything because we are wrong in our conclusion. And so we're telling people that isolation is working when it's really not. And then the danger of this would be we would say that the isolation isn't doing anything, but it really is. I think actually my opinion is this type of error is worse in this case because we were really doing something to combat the zombies. It was actually working. We were decreasing the rate of zombies. And now we're all just going to give up on that and just go home, even though it was working. So I think in this case, the type 2 error is a little bit worse. So the next question here is, we're asked to decide on what a reasonable level of significance would be. So the level of significance is the acceptable amount of risk of a type 2 error. So how comfortable are you with coming to a wrong conclusion if this is the potential mistake that you're making? So if you're doing a hypothesis test that's about something that's not very serious at all, like some students are doing, like wasn't there some examples about Chick-fil-A? Chick-fil-A? So if you're doing a study about what type of Chick-fil-A sauce people prefer, then the risk of saying that everyone's favorite sauce is barbecue when it's really ranch is not that big a deal. They're probably still going to have plenty of sauces for people to choose from. So that's a time where you're okay with an acceptable amount of risk. And you could maybe choose like 10% risk or something like that. But if you're doing something that's maybe a little bit more serious, like blood pressure medication or anything where people's lives are on the line, then you're going to want to have a small amount of risk, like 1%. And then our generally medium allowable amount of risk is 5%. So think about your project and think about what could go wrong in the real world if you come to a wrong conclusion. And if that's not a big deal, then you're going to choose a large level of significance. And if it is a big deal, then you're going to choose a small level of significance. In my mind, wiping out the zombie hordes is a very big deal, and I don't want to come to a wrong conclusion about this. So I would choose a small level of significance in my example. Question 3 asks us to write the null hypothesis and alternative hypothesis for each of the two parameters. Here are my two parameters that I chose. I chose the proportion. So this is the categorical variable. So the question that we would be asking a JCCC student is, are you a zombie? And they would answer that with a word, yes, if they were a zombie. I don't know, would they say ugh or brains or something? I don't know. And then the numerical variable is the average number of brains eaten per day. So the more brains that are eaten, the more zombies that there are on campus, and the less brains that are eaten, the less zombies there are on campus. And this is a numerical variable because if you asked a student, how many brains have you eaten today? That's what zombies do. I don't know if you guys know that, but zombies eat brains. This guy's got a crack in his skull because somebody ate his brain. Wait, hold on, I gotta fix this. This is important. There we go. Now it really looks like he's got a crack. What was I? Yeah, okay, so both of these things are measures of the number of brains eaten per day. For question 4, we're asked to explain why we chose left-tailed, right-tailed, or two-tailed alternative hypothesis. So here are my two alternative hypotheses. One is that the proportion is less than 24%, and the other is that the average number of brains eaten per day is less than 9.4 brains. And here are the three choices for left-tailed, right-tailed, or two-tailed. Each of them correspond to the different possibilities for alternative hypotheses. In my problem, I chose a left-tailed hypothesis because I think that the isolation has decreased the rate of zombies. So I chose left-tailed because it makes sense that isolation, less people interacting with each other, would cause there to be less zombies. Questions 5 and 6, I don't know, in retrospect, I don't know if I really needed to make these two separate questions. What you're asked to do is basically just interpret the results here. So we just need to write some kind of technical conclusion. And I've done that here. We have significant evidence at the 1% level that the population rate of zombies is less than 24%. So we're asked to do this. We have evidence here. This is because we rejected. So if we did not reject, then we would not have significant evidence. This 1% is because I chose 1% up here in this part because I think that my hypothesis test is serious business. And then here I am. I've actually only done this for one of my two parameters. My two parameters are the rate of zombies and the mean number of brains eaten per day. So I'm just actually not completely done with this because I should also have one that says we have significant evidence at the 1% level that the mean number of brains eaten per day is less than 9.4 brains. I'm happy to help you if you have questions on this. Hopefully this gives you a better idea of what's expected of you in the project. I'm going to post a PDF of these notes on Canvas, so please reach out to me if you need any help with this or have any questions.